many ways, you know. You could take the two equation pair the traditional way. However, in this case, I always recommend you spend few seconds to meditate a little bit about the equation. For example, the first equation is x plus y plus c equal 5. So the coefficient is 1, 1, 1, positive 1. And equation 3, we have similar because the same coefficient is 2, 2, 2. If you divide by 2, because it's even number, right? Divided by 2, divided by 2, divided by 2, divided by 2, the equation 3, you know we can do that, right? X plus y plus z equal minus 3. And this is my new equation 3 after the division. When you compare this equation and this equation, I can see clear a contradiction, because one thing is x plus y plus z equal negative 5. And the same thing equal negative 3 is impossible. Now, no solution. Okay, so you get the same conclusion. Suppose que some students say, bueno, professor, okay, I understand that. However, I don't see that. Okay, no problem. If you are doing a different way, you get the same conclusion. But maybe it's a long way. Good? Okay. Any question? No? Okay, let's move on now to the 21. 21 and 22 is a little bit complicated. Not complicated, but slow. No. It's basically one matrix given. 1, negative 3, negative 5, 2, 2, 5, 2, negative 5, sorry. 2, 5, 3, negative 5 again, 4, 6. Entonces, and the questions say, perform the row operation on the given augmented matrix. So this is augmented matrix, I suppose, is associated with the one system of equation, and you need to perform several row operations. Entonces, the idea behind the Gauss-Jordan algorithm is the row operation. No, you are doing several. I try to omit this because it's very, very tedious. But let's do at least 2 problems of this to understand this idea. So, and the operation is given, no? Is, for example, the first row operation that they want you perform is -2 R1 plus R2 storage in R2. Okay, you need to be familiar with this notation. The notation is the capital, so the typical format for the row operation, there are several, but the most important row operation is this. You have, for example, one factor, que es negative 2 in this case, one factor, in our first case is negative 2, no? You multiply this factor times the entire row 1. The entire row 1 is this, no? Row 1, everything, bam, 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 4 multiplication, and plus row 2, the corresponding, of course, in the same column. Yeah, so the element que corresponde in the row 2 is 2, corresponding with the 1, negative 5 corresponding with negative 3, and the same column, no? And this new information you store in R2. The notation is we use a little r for the old row, and capital is the new one can you replace. Okay, therefore, the new matrix after the transformation is, well, I copy row 1 exactly the same, because row 1 participate in the game, look at that. However, the information gets changed only is R2. And row 3, no participate. Just stay the same. The only row get changed is row 2. Let's do in the operation here. Is, for example, the factor is negative 2, because this is given. In the real life, no. In the real life, the algorithm discover what is the factor can eat. But it's obvious que es negative 2 because it's the same number here. Look, but with the opposite sign, always. So for example, so you multiply negative 2 times 1, get the first element in the row 1, and you adding the corresponding element in the row 2, get 2. That's 0. And this is 0. Again, minus 2. In this case, the row is negative 3 plus negative 5. No? Okay, I am using the second element in the row 1. This is positive 6 minus 5 is 1. And 1. The second is negative 2 times negative 5, que es the third element in the row 1. Plus 2, que es the corresponding in the same column of the row 2. Entonces negative 10, bueno, negative es positive, entonces positive 10. Positive 10 plus 2 is 12. This is 12. And finally, minus 2, que is the same factor for this operation, is multiplication by 2, que is the last element in the row 1, plus the corresponding que 5. Well, this is negative 4, and this is positive 5 is 1. They did the transformation. This is elementary, step by step. That is a reason that this is very, very tedious. And we are doing one shot using the reduced row echelon. Suppose, what's the next step that the algorithm will discover? I need 0 here. But no, in this case, no. Well, yes. Because, look, the next operation is minus 3 R1 plus R3 storage in R3. Okay. So now I don't touch, well, touch, pero participate, but no, doesn't change. The only row that change is R3. So 1 and 2 stay the same. Now row 3. Row 3 is negative 3. This is negative 3, que is a factor. Multiplication by this, que is the first element in the row 1. Well, it's negative 3. And negative 3 plus 3, que is the corresponding element in the same column, is 0. Okay, this is the idea for the algorithm. Entonces we continue the same. I have the solution here. Is 0, 1, 12, 4, 19, 0. And the last row operation is que they want is 5, positive 5 is the factor, R2 plus R3 stored in R3. So in this case, the only row that change again is R3. Therefore, row 1 and row 2 stay the same. Now let's do at least the first one. We multiply 5 times 1 is 5. 5 times 0, because the row 2 is 0 plus 0 is 0. Entonces 0 is 9, is 79, and 5. Okay, let's do it. Let's say 5 times 0, this 0 is this 0, plus 0, this 0, is equal to 0. 5 times 1 plus 4 is 9. Look, it's 9. 5 times 12 is 60, plus 19 is 79. And finally, 5 times 1 plus 0 is 5. Yes, it's 5. Clear or confusing? In this case, they want that you are doing 1, 2, 3 row operation. 1, 2, 3 row operation in this order. And this is sequentially. You have original matrix, you perform row operation, 1, and on the second, not the original, you perform the row. Can you see the entire thing? Yes, of course. Yeah. I suppose in the test I put one question like that. But you relax. You are doing step by step, checking with the calculator the operation, and that's it. Any question, guys? Do you understand the idea? Remember, in the real life, never we using this by hand. No, we are putting there are another graphic calculator that we can do in this way. You indicate the row operation and do a little step by step. But in the real life, we don't need that. We need the completed process, and the completed process doing totally the row operation that you need to convert to echelon. Let's go to a 22. Okay, it's exactly the same, but it's too long because it's a huge matrix. Is 4 by 5. 1, 1, negative 1, 1, 3, 0, negative 5, 1, negative 2, 0, 2, 0, negative 3, negative 4, and 3. Negative 5, 1, 0, 5, negative 4. And this is the matrix. The dimension is 4 by 5. 4 row, 5 column. Because it's augmented matrix, I suppose. And the row operation that they want you perform is minus 3 R1 plus R3 storage in R3. Because I suppose in this moment somebody, not me, doing this row operation and create this 0. Now. Wow. No. Well, okay. Don't worry. In this moment is let me copy. The majority of the matrix doesn't change. Only change in the row 3. So I copy the rest exactly the same. Row 2 exactly the same. Row 4 exactly the same. And the only guy que change is row 3. Entonces 1 minus 3 the factor. The factor is minus 3 times 1 is minus 3 plus 2 is negative 1. Negative 3 again times 1 is negative 3, and negative 3 plus 0 is negative 3. And negative 3 times negative 1 is positive 3, and positive 3 and negative 3 together is 0. And negative 3 times 1 is negative 3, and negative 4 is negative 7. And negative 3 times 3, no? Is negative 6, and negative 6. Let me see, negative 6. Okay, negative 3 times negative 3 is negative 6, and negative 6 plus 3 is 3, no? It's minus 3. Okay, and they want another more. que es de phi R1 plus R4 storage and row 4. Okay, in this case the row 1 stays the same. The row 2 stays the same. The row 3 stays the same. And the only guy can change is the row 4, no? Let's do at least one. So it's easy. Let's look. This is 5 times 1 because we are working with the row 1 first. The factor is 5. 5 times 1 is positive 5, minus 5 is 0. 5 times 1 is 5, plus 1 is 6, no? And 5 times negative 1 is negative 5, plus 0 is negative 5. And 5 times 1 is 5. 5 plus 5 is 10. And finally, 5 times 3 is 15. No? 15 minus 4 is 11. Que es the option A. The answer is the option A. Make it zoom. In the test, you can see one question like that. Okay, 22, no? 22. Uh-huh, 23 now, 23. Any question, guys? Do you understand very well the idea behind the row operation? This is the foundation. Okay, this is the foundation of the Gauss-Jordan algorithm. No? Manipulate matrix by matrix. It's too long process, but it's okay. We can do it automatically using the software. Okay, so let's do using the software. Suppose 23 now. 23 is minus 2x minus y minus 6c equals negative 77. Equation 1. Okay, minus 7 x plus 3z equal minus 29. Equation 2. 9y plus z equal 72. Positive. Okay, this is my system. And they want easy, not complicated. Can you solve it using the matrix? Of course, don't do the tedious algorithm. No, you put in GeoGebra, and GeoGebra helps you to solve that. The first thing I want to see in the test is you write the matrix associated. Okay, minus 2, minus 7, 0. Negative 1, 0, and 9. And negative 6, 3, and 1. And you separate by the line. You put augmented matrix, include the number in the right hand side. Okay, so you go to the GeoGebra and you apply the algorithm reduce row echelon form. I want to show you now in GeoGebra. Okay, I switch into GeoGebra. Look, let me see. Wow, there's the review. The first part. No, this first part. Okay. This. Okay. Let me share screen. Okay. I suppose in that moment you see GeoGebra, right? This is the matrix. This is the matrix. Remember the organization of GeoGebra. You have the algebra, we have the CAS. CAS is computed assistant software, the symbol in mathematics, CAS. And this is CAS, sorry. And this is the algebra. And it doesn't matter the order. Doesn't matter the order. You type in the number in the spreadsheet. You press right click. No. You select everything. Right click, create matrix. I did that. And when I did that, you get this answer. Okay, this answer. And the case M3. Entonces now the reducer row echelon form M3 give me this information. That's the thing I want to copy in my paper, no? In my whiteboard. In my whiteboard, I get the answer. I get the answer. Look, 1 0 0 0 0 0 0 1 and 8 7 and 9. Therefore, you immediately recognize that we have in front of the problem of the unique solution. The idea is clear because we have the identity matrix here, 3 by 3, and x equal 8, y 7, and z 9. End the story. Like at the option B. You see option B, no? Yeah, option B. Okay. Let me ask a question. Are you familiar with the GeoGebra, right? I know that you need to practice, but you know what is the idea? No? The idea is you go to the view. Let me come back again to GeoGebra. You come back to the view. Okay, view. Okay, look here. Okay, you come back to the view. Wow. Okay, suppose this is the GeoGebra environment. You click here in the three horizontal line, and you select MVU. You select the most important is algebra, CAS, and spreadsheet. When you have this window open, or this view open, you type in the number inside the matrix, you select everything, right click, create matrix, and when you have the matrix in algebra view, you go to the CAS view and you type in reduce the row echelon form, and you put inside the argument of that function the name of the matrix you want to work. Okay, this is the idea. Are you familiar or no? I know that you need to practice. Of course, you need to practice, you know? But I explained in the lecture moment. This is review. I suppose you know, right? Someone. Okay. I understand. You have to practice, guys. This is the idea. I cannot do for you. This is your moment that you try to do by yourself. Now, so far, until now, I omit that part. I don't remember. See, when they sent the review packet, I sent a link connected with the GeoGebra. I suppose yes, right? So you can check it. So in order to don't waste the time, I put directly so far to this problem 23, 24, and so on. I put it directly the original matrix. I put the reducer row echelon after the GeoGebra. I don't need to go to GeoGebra because the process is the same, right? And the important thing now is the interpretation of this. So the interpretation is clear. Look, you have the identity matrix. No extra column, no extra. This is the column of the X, this is the column for the Y, this is the column of the Z, And when you translate each row to equation, you get only x equal a because we have no y and no z. It's missing. Like y, the second equation gets the second row is y7 and z. Okay, let's practice. Let's practice this. Let's do in the problem 24 now. 24 now. Okay, in 24 we have ax 24 minus 7y plus 3z negative 122. It's equation 1. Negative 40 x plus 35 y minus 15 c is equal 610. Equation 2. And 16 x minus plus 6z equal negative 244. This is the system is given. I need to solve it. The first job is write in matrix way 7 3 bar minus 122. The second is minus 40 35 minus 15 16 16 negative 14 6 and minus 244. I put in the algebra, I apply reduced row echelon. Remember, it's reduced row echelon 4. And this is the acronym, reduced row echelon 4. And you put inside the matrix M, I don't know, 4. Can you edit in algebra? Okay, this is the answer. I want to copy the answer. The answer is weird. Look at that. The interpretation is the most important. S1 is negative 7 over S3 over 8. Line minus 61 over 4. And amazing happened. Okay, this is 0, 0, 0, 0, 0, 0, 0, 0. Now, what is the interpretation of this? Well, the interpretation is the row is completely 0 is because the elimination process, the Gauss-Jordan algorithm, discovered that two equations are dependent of the another equation. And you see it's a little bit logical because if you multiply, for example, this equation, but at the beginning I don't see, you multiply 8 times negative 5, the row 1 by negative 5, you get the row 2. Now, if you multiply the row 1 by 2, you get the row 3. So elimination process discover okay, two equations are totally independent of the first equation, and you can delete that part. This part is totally irrelevant. It's not important. If you want to write only one matrix like that, can contain, for example, 1 row and 4 columns. This is 1 by 4 matrix. This. Entonces now, remember, entonces, this is clear that we have infinity many solutions. We have infinity many solutions. To discover the idea for the infinity many solution and the idea of the how many free variables we have, remember, infinity many solution involve free variable. The format is clear. You try to find the identity matrix, okay, and the rest of the column after the identity matrix represent the free variable. Okay, represent the free. And okay, sorry, this is the vertical line, the traditional vertical line. This line, and stay the right hand side. But the free variable is the extra column after the identity matrix. This identity matrix maybe is dimension 2, dimension 3, but in this case, dimension 1. Wow! Because it's just one easy or elementary one. You can interpret it. And the free variable is this block and this block. ¿Qué es this? In this case 2, no 3. Entonces, X, Y, and Z. We have 2 free variables. Okay? How you express the final answer? Well, it's easy. You express the final answer like that. Look. You copy the equation 1, que es de row 1, que es X minus 7 over 8 Y over 8 E equal negative 61 over 4. And you solve the only known free variable we have, que es X, as a function of the free. The minus 61 over 4 plus 7 over 8 Y minus 3 over 8 Z. Okay? Now, how you write the solution? Well, there are many ways to, well, not many, but some way to express the answer case. The most easiest to understand is you express X comma Y comma Z, no? But who is X? Is this expression. It's minus 61 over 4 plus 7 over 8Y minus 3 over 8Z. And this guy is a free variable. Entonces you indicate like a Y and Z. End the story. This is one possibility to express the answer. Another possibility is the traditional way in which you formally, you open the braces, you understand that my solution belongs to the R3 X comma space such that X is equal, you copy this expression again here. You separate by comma, Y and Z are all real numbers. Totally free. Okay, either way, guys. Do you understand the idea? Any question? What is the confusing part? Come on, confusing. That was 23, no? 24 example. Do you understand this? So everyone answer me. I understand. Okay, yeah, many understand. Who more understand? Everyone understand? Okay, strong understand. Okay, let's practice a little bit more. Let's practice more example of this. To say, no now, you don't need to do now. You only follow me. You what? Good, very good. Everyone understand? Okay. 25 now. 25th. Where the GeoGebra do? Repeat the question. I am looking for another place. I don't see the last student asked me something in the chat. Activate the microphone and ask me directly. 25. X minus Y plus 3Z equal negative 2. Equation 1. Plus C equal 1. Equation 2. X plus Y plus 5Y plus C equal 26. Equation 3. Okay, exactly the same. I have no idea at the beginning. See, it's unique solution, infinite dimensional solution, or no solution. You write the matrix associated with the system. 1, negative 1, negative 2, 2, 0, 1, 1, 5, 1, 26. This is my matrix. By the way, the dimension is 3 by 4. and you apply again the reduced row echelon form. And the answer is 1 0 0 0 0 0 no 1 0 0 0 1. In the right hand side we have 0 5 and 1. Okay, now interpretation, is the most important moment. I can see okay, we have here the identity matrix dimension 3 I3. We have no extra block, extra column, therefore unique solution, and x is equal 0, y is equal 5, and c is equal 1. End the story. Option B. Clear or not clear? Okay, let's do one more, because the next one, 26, is interesting. Okay, let's see what happened. 26. 26 is a huge system, 5x plus y equal 1. This is equation 1. 2x minus y plus c minus w equal 3. Equation 2. And z plus w equal 7. Equation 3. Okay. We have 3 equations, 1, 2, 3, but you have 4 unknown. This is a classical example in which this system is underdetermined because you have more unknown than equation. No? So we have lack of information. You never expect unique solution. Oh, infinity many solution maybe. Oh, no solution, but never unique solution. Okay, I write the matrix. The matrix is 5, 1, 0, 0. Okay, you want to make sure to organize this is you put it here the column for the x, the column for the y, the column for the z, the column of the w, and the column for the right hand side number. Yeah, I translate my first equation like a matrix language, like in my first row. The second is 2, negative 1, 1, negative. And the last is 0, no, x and y is missing, 1, 1, 7. Okay, that was easy or relatively easy. The rest is typing that number in the GeoGebra in the spreadsheet. Right click, create the matrix, and apply the function or algorithm, reduce row echelon. Entonces the answer is 1, 0, 0, minus 2 over 7, negative 3 over 7, 0, 1, 0, 10 over 7, 22 over 7, 22, 22 over 7. This is 2. 0, 0, 1, 1 again, 7. Okay, this is the answer after the apply the algorithm. No? So I can see interpretation. Again, I see, wow, look at that, identity matrix. Identity matrix, dimension 3, 3 by 3, 9 numbers. However, we have extra column that represent the free variable. By the way, this is the column of the x, this is the column for the y, this is the column of the z, this is the column of the w. So we interpret a w as a free variable. Okay, you say, well, always the last variable is the free. No, no, no. Okay, great. See, you organize in different way, maybe you get different, no, the same idea, but you do declare another. So the definition, what is the free variable, depending on the organization that you set up in your matrix, no? But the central idea, the most important, is that this system have infinity many solution, and we have only one free variable, and you express the rest of the variable, in this case x, y, and z, as a function of w, but not necessarily always should be the same, depending the initial organization for the matrix. Okay, entonces you translate, entonces you, for example, the first row is x, no y, no z, minus 2 over 7, w equal minus 3 over 7. Entonces you isolate the non-free variable as a function of the free, minus 3 over 7 plus 2 over 7, w. This is 3. Let's do it row by row. The second is y plus 10 over 7 w is equal to 22 over 7. Therefore, the equation can stay, the relationship between w and y is 22 over 7 minus 10 over 7w. And finally, z plus w equals 7. Therefore, c is equal to 7 minus w. Entonces, in this case, we have infinite many solution. We have only one free variable. No, we always have it, but the most common case is only one free variable. And basically, our solution set is the object, the mathematical object, that living in the 4-dimension context, because we have four variable x, y, z, and w. So basically, the solution set is some mathematical object living in the 4-dimension space that belong to the R4, such that x is equal to something, y is equal to something, z is equal to something, and w is free. Okay, free means all real number, you know. Numbers. Entonces, in this case, I copy 3 expressions, que es this expression, and this expression. That's it. This is the interpretation. Any question, guys? Entonces, in this moment, you are capable to face any engineer problem, que, for example, have 15 equations, 15 or no. Okay. I organize my equation in matrix form. This is a long process, and you need to organization this. And normally in the equation and the real life contain a lot of zero because some variable is missing. Now you put it in matrix form. You type in one by one in the GeoGebra. There are another software. To do the same job, and apply the reduced row echelon. This is one possibility. Not the unique possibility, but this is one possibility. Okay, I like so much. Okay, let's move on to another topic. Let's move on to the determinant. I want to explain in detail now. Determinant is a completely different idea. It's another method. At the beginning of the last century, the mathematicians don't be strong in the matrix. However, develop the determinant. The determinant is another possibility, another point of view for solving a system of equation, no? There's some people, I found a lot of people is fan to the determinant and don't like the matrix. No, matrix I don't understand very well. I prefer determinant. Okay, why? For 2 reasons. Reason number 1 is always we working with the square matrix, 3 by 3, 4 by 4, 2 by 2, and also and also the it's just numerical. Okay, you compute the number. So the answer for this determinant is a number. Bam, 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 bam. Okay. Entonces no free variable. No, no. Okay. So what is the idea behind? Well, we can do by hand at least one example. Well, I don't know. And also we can use GeoGebra to compute the determinant. Let me explain at least one by hand, 3 by 3. This is a little bit crazy, but so you take calculus 3, you need to solve in several determinant 3 by 3. But okay. Okay, what is the formula? What is the formula? Well, the 2 by 2 is easy. 3 by 3, no easy, no easy, no easy. So you take, okay. Let me try to explain the general formula. A11, A12, A13, A21, 22, 23. I'm using double subscript to indicate the position for the element inside the determinant. This is 3, 1, 3, 2, and 3, 3. The first number indicates the row. This is row 1, row 2, row 3. This is column 1, column 2, column 3. So this guy, row 1, column 1. This guy is located in the row 2, column 1. So what is the idea? There are several, no infinity, but there are a lot of, I suppose que es 9 possibility, because it's 3 by 3. To expand the determinant. The most common, not always, but the most common is using the row 1. So you navigate por ahí, pam, pam, pam. But you can use in row 2 or row 3 or column 1, column 2 or column 3. And the answer, unbelievable, doesn't change. So you copy A11. A multiplication by the cofactor 1 can few seconds. I want to explain who is this guy. Plus A12 by the cofactor 1, 2 plus A13 times cofactor 1, 3. This is one possibility. You can use it if you want the row 2 or the row 3. Or the column 1 or the column 2 or the column 3. The way que you consider better. Entonces, bueno, cofactor 1, 1 is 1. It's obvious, right? It's obvious. It's this element. Sorry, A11 is 1. No, cofactor 1, 1 is the, okay, cofactor 1, 1, a minor 1, and the corresponding sign can maybe a plus or minus. That depending, okay, cofactor 1, 1 is equal plus or minus a minor 1, 1. Who is the minor 1, 1? Bueno, es the new determinant que es minor, is decreasing the order, que es formed when you delete the row 1 and column 1. Because 1, okay? And so we have a new determinant que is multiplication, this 4, -1, 5, 5, 5. Okay? I did that part. Now, let's move on to the element 1, 2, que es this element. Entonces, in this case, es a cofactor 1, 2 is minus 1, 2. Okay, in this case was positive. Okay, in this case was positive, it's the same. But in this case, it's negative. So how do you know? Well, okay. This is complicated to explain. No, not complicated. Look, is the sign of the cofactor depending the position. So, for example, the first is positive. The second is negative, que is exactly what we are doing now. The third is positive, alternating. Negative, positive, negative, positive, and negative, positive. One, there a formula for this. Yes, yes. One factor is cofactor ij, when the ij is totally arbitrary. It's a minor ij and -1 raised to the I plus j power. In other words, I discovered que I plus j is even, the cofactors have the same sign. Entonces, 1 plus 1 is 2. Es even. 1 plus 2 is 3. It's odd. Entonces, negative. That's it. There are many mnemonic devices to remember this. No stupid, pero elementary idea. Okay, entonces, the second cofactor, the second guy is -1. Remember que es minus. This one is this one, and the sign is the cofactor sign according to the position, multiplication by the minor, and this minor is formed when you delete this and this. Then we have -2, -1, -3, and 5. Okay, good. Now finally, to finish the row 1, I have +2. In this case, the position is 1, 3, and 1 plus 3 is 4, it's even, entonces positive. And you delete this and this, and stay alive. -2, 4, -3, and 5. Okay, entonces you know the 3 by 3 is very complicated. You can imagine 4 by 4, no? It's crazy. Now your multiplication 2 by 2 is super easy. It's 20 plus 5. Okay, welcome from that. 4 times 5 is 20, and 5 times -1 is -5. Remember, when you multiply in this direction, doesn't change the sign. When you multiply in this direction, change the sign, and double negative become positive. Minus -10 minus 3. Because when you multiply in this direction, we have one negative, entonces negative. But when you multiply in this direction, we have 3 negative. So the 2 negative of the value, and 1 extra negative is when you are doing the multiplication. This is the mnemonic divide to remember this, no? Plus 2, and when you multiply this and this, is -10, and when you multiply this and this, is +12, because we have one negative and one negative become positive. Basically, it's 25 plus 13, negative, 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 13, negative, negative, but positive in the front is positive, and this is 2 times 2 is 4, no? -4, -4. Is -4 or +4? A ver, I'm making mistakes here. Yeah, a ver. No, es plus. Es plus. Es plus, ¿no? Es plus. Es plus. Entonces 25 plus 17 is 34. Exactly the same answer without no complication. We can do that in GeoGebra. Let me show you at least one. Let me pause for a moment. In this moment, please, do you see the idea? It's complicated. I know it's hard, a little bit hard. No, hard. Hard is not exactly the word to define this idea. It's algorithm. It's the organization of the number, right? And you need to memorize this? No, of course no, because in GeoGebra we solve it in 1 second. Okay, let me try. Let me switch into GeoGebra. This is the last transfer for the GeoGebra I want to do today. Okay, wait a second. This is no. It's the second GeoGebra. I have 2 folders of the GeoGebra. Look. Okay, share screen. Okay, I suppose this is good. Do you see now? Okay, the example I'm doing now was, look, this example. I type in like a matrix, 1, 1, -2. I right click, wait, select everything, right click, create the matrix. Yeah, I did that. This is my matrix, right? Now, in computer assistant software class, I type in determinant. Look at the determinant, and you put inside the matrix N1, and the answer is 34. End the story. I finish. Okay? So we're using this idea every day, anytime that we need to. Right? Do you see that? Okay. Let me try to transfer it one more time to the whiteboard. Good. In this moment, I suppose you see the whiteboard, correct? Let's do in 28. Let's do in 28. Let's do in 28. And 29, why not by hand? But I using one good strategy. I want to illustrate you. Computer determine this. So I take advantage. Okay, the majority of zero. Because in the real life, when you have determinant of the real system, we have a lot of zero. And you try to find what is the column or what is the row that contain the more amount of zero. In this case, by coincidence, is the row one. So you take advantage. This zero, it's obvious that you have only one cofactor alive because the rest is 0 times something. So 3 times the cofactor gets formed when you delete this and this case 6, 4, 9, 8. Because the rest is 0, no? 0 times something, cofactor 1, 2, no? Plus 0 times cofactor 1, 3. I don't care, this guy. Okay, now is 3 and multiplication. Multiplication is 48 plus minus 36. 48 minus 36 is 12, and 12 times 3 is 36. That is the answer. So you try to take advantage. This fact. When you have 0, you select the row or the column, because you can use a row or column to compute the determinant. This is the new thing in determinant. In matrix, no. In matrix, you always working with the row operations in matrix. In determinant, no. In determinant, we working independent row or column, either way you prefer. 29 is similar. No, it's not similar. It's different. We're using this property. Look, we're using that property. Sorry, professor, I have to go early. Okay, Yami, no problem. 2, 5, 5, 1, 2, 3. O sea, when this situation happens, I encourage you, can you try to put in your algebra, but the answer is 0. Why is 0? When you have 2 rows or 2 columns equal, you immediately, it's one important property. Same column or same row is 0. Okay? And you have same column or same row equal to 0. The same is the determinant is equal to 0. Okay, let's do it now to the Kramer rule. Que es the application, no? The application for the determinant is solution for the system using Kramer rule. And remember, Kramer rule say Kramer rule. Kramer rule say, okay, it doesn't matter the system that we have, the x value is dx divided by d. And d is the determinant, the main determinant formed by the coefficients in front of the variable. And dx is the same d, but you replace, suppose this is d, and you replace the column of the x by the right hand side number in the system, and you compute that. Finally, you divide and you get the, like y happened in the y is equal to dy over d. To say you replace the column of the y only by the right hand side number, and this stays the same, of course, and the x doesn't change, it stays the same. This is a Kramer rule. Some people lie this way. Okay, I respect. I don't, but some people lie. Okay, suppose the problem number 30. Problem number 30 say 5x plus 9z equal 52. Equation 1. Minus 6x plus 3y minus az equal minus 42. Equation 2. 2x minus 6y equal negative 14. Equation 3. Okay. Let's solve it using Kramer rule. Okay, what is the organization? Well, the organization is, first of all, you compute d. Capital D is the determinant formed by 5, 0, because in the first equation y is missing, and 9. Only coefficients in front of the variable. Negative 6, 3, negative 8. 2, negative 6, 0. This is D. And you put in your algebra, the answer is 30. It's too long process, but okay, I understand. Who is dx? Well, dx is the same determinant, but you replace the column of the x, que is the first one, by the right hand side number, que is 52, minus 42, and minus 14. And the rest, no, stay the same. I just copy and paste. I put in your algebra again, I compute that, 150. dy is exactly the same as, but you replace now the column of the y by the right hand side number, and the rest stay the same. Now this is 52 minus 42 minus 14. 9 minus 8, 0. I put in your algebra, I compute the answer 120. And this z is now 5 minus 6, 2, 0, 3, minus 6, and you replace the c column now by the right hand side number, que 52, minus 42, and negative 14. I compute that, and the answer is 90. Post. Now, finally, x is equal division 30, no, 150 divided by 30, fi. Y is equal 120 divided by 30, f4. And c is 90 divided by 30, f3. And the solution is the triple order 5, 4, 3. Like the option C in the handout. Do you understand the organization, guy? Do you understand the organization? Kramer rule. Clear Kramer rule or no? Are you boring? Tedious? Or interesting? Clear. Okay. Let's move on to the one a little bit sophisticated topic, is determinant again, but using the property. So we can apply some property to manipulate determinant. For example, one property that we studied was when the column or the row is the same, the determinant is 0. But we have another property. Suppose this example is giving one determinant. By the way, we cannot using GeoGebra or any graphic calculator because it's a variable, it's a literal. Suppose that this information is given. Suppose that somebody plugging in the variable, I don't know where's the value, and the answer is 38. And the problem, this is given. I need to calculate another determinant que es similar somehow, x, y, u, v, and 1, minus 3, and we have minus 3 here. And the last column is weird, is z minus x, is w minus b, ¿no? A ver. Minus u. This is u. And negative 2. Entonces you need to know that when you perform columns or row operation, this is a completely new idea. Remember, in matrix we are always using row operation. In determinant, no. We can manipulate a little bit different, horizontal or vertical. So in this case, for example, the thing I can see here is that the column 3, column 1, column 2, column 3, the column 3 minus the column 1, because let's look, z minus x, w minus u, negative 1, minus 1 is negative 2. We get the column 2. And you store in the column 3, the new column 3. This is the new one. When this situation happens, it's a column operation, the value of the determinant stays the same. Okay, this is a property that we are using. You can perform on any determinant, column operation or row operation, and the value of the determinant magically stays the same. And look, remember 1, 2, 3, 4, 5, 6, 1, 2, 3. Remember this determinant, the answer is 0. It's 0, professor, because we have two rows exactly the same. But if you perform row operation and you subtracting, 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0, and you store this 0 in the row 3, for example, where come from this 0? Was 1 minus 1, 2 minus 2, 3 minus 3. Es obvio que the answer is 0. Okay, entonces when you perform maybe column or maybe row operation on the determinant, the value stays the same. This is the idea. Okay? However, this is the only property that have the determinant. No. We have another more important. Okay, any questions so far? Do you understand this or no? Sure? Okay. Let's move on to the 32. It's a little bit different. 32 is a little bit different. 32 is one determinant is given. Okay, it's XYZ, XYZ. UBW, UBW, UBW. 1, negative 1, 1, negative 1. Negative 3 is given, is equal 146. Yeah, I need to compute another is given. I need to compute another guy. Compute another guy que es similar, no? So if somebody do row operation or column operation in this determinant, que es XYZ, 3U, 3B, 3W, and 1. Wait a second. wait a second, is the original I need to compute it is 3u minus 1. Okay, this is wrong. This is wrong. It's x plus 3, y minus 3, and z minus 9. 3u minus 1, this is u. 3b plus 1, 3w plus 3, and 1 minus 1 and minus 3 stay the same. It's the same row. Okay, because I need to, manipulate a little bit step by step. For example, let's do it in the another order. Suppose that for the given information, I multiplication, I can see 3b, 3u, 3w. So you multiply, for example, x, y, z, and you multiply 3u, 3b, and 3w. So if you multiply one row or one column, entire column, by one number, the same number, of course, yes, different number, no, it's crazy. The value of the determinant is also multiplied by the same number. That's 3 times 146 is 438. Okay, it's the only thing I did. Multiplication any row or any column by a scalar, it's a number, just a number. The value of the determinant is affected by this number. This is completely different to the matrix. The matrix is not working like that. The matrix is not working like that. But in determinant, yes. If you multiply only one column or only one column, not necessarily multiply everything inside the determinant. No, so you multiply everything inside the determinant, you multiply by 9 times this factor because we have 9 elements. Or 3 times. Now, this is the answer, no. Why no? Because I need to modification a little bit. Suppose I see here -1, +1, and 3. So basically, we are doing here a row operation. What kind of row operation on this? When we are doing the row 2 minus row 3 storage and the row 2, because I want to modification the row 2. What do you do? 3.14. The reason is because this is my original determinant, correct? I try to manipulate in order to look like similar to this. And the first thing I saw was, look, 3u, 3b, and 3w. So I suppose, I don't know if I'm wrong or right. I multiply the row 2 of the given determinant by 3. So using the property I know, okay, when you multiply one row or one column by the constant, the value of the determinant is multiplied by the same constant. This number is this number, and this 3 is this 3. Got it? This is the easy part. This is the easy part. Now the complicated part, in my opinion, is try to advance. So I have this. This is similar to this, except okay, we have here -1, +1, and +3. So I propose you the following. Row operation. This is a row operation, no column operation, row operation. The row operation is, well, the first stays the same. No. The first stays the same. Okay, look. X, Y, Z stay the same, like that. Now use subtraction. 3u minus 1. 3u minus 1. 3b minus minus. Entonces 3b plus 1. Okay, your multiplication 146. Your question is 146 times 3. It's 438, huh? It's multiplication. Time. Here, multiplication. And finally is 3w minus 3 que es plus 3. Entonces 3w plus 3. And this stays the same. I finished, no? Oh, remember the manipulation was, we have the first stage, the second stage, and the last stage is do something in order to have 3, 3, and 9. Okay, basically it's another row operation, that is row 1 plus 3 times row 3 storage in row 1. You need to use in your imagination. Entonces, look. The row 1 change. The row 2 no, stay the same. The row 3 no, stay the same. But now you change the row 1. And the row 1 is multiplication by 3. 3 times 1 is 3 plus row 1 que es x plus 3. 3 times negative 1 is minus 3 plus y is y minus 3. And 3 times negative 3 is negative 9 plus c is c minus 9. Entonces you get exactly the same identical determinant to the guy that you need to compute. And remember no. I see in the last example, when you compute the row operation or column operation, the value of the determinant stays the same. So this is stay the same, and this is stay the same. Doesn't change. And this is the final answer. Okay, let me try to summarize. One determinant is given. One value is associated, 146. You need to compare another. I see that they are similar, but not exactly the same. And you using your imagination and your common sense and apply several properties. And you apply the first property is multiplication and the row 2 by 3. Because I saw in the last one, the coefficient in front is 3. 3u, 3b, 3w. So one property say, when you multiply any row or any column by a number, the value for the entire determinant is just multiplied by the same number. Okay. So 146 times 3, 438. Good. The rest is manipulation in order to look like similar to the new determinant I want to compute. The first was row operation between row 2 and row 3. Because row 3 is nice, because row 3 is just numerical. So see, if you subtracting, so you get the new row 2 is exactly the same of the row 2 of the determinant I want to look for. Finally, the first row is not the same. But I can see that you apply another row operation, and between row 1 and row 3, a multiplication by factor 3, we get the row 1 new. Now, my new determinant is exactly the same. The determinant I want to find the value is when you perform row operation or column operation, unbelievable, magically happen. Okay, the determinant is the same value. Okay. It's something weird, right? Oh no. I know. The student don't like that part normally. Okay, I don't know. See in the test I put one question like that, no? In this case, unfortunately, we cannot use in the GeoGebra because it's okay. Let's do in the multiplication. Okay, 33 now. 33 is multiplication. So operation on matrices. 36 -9 -8, sorry, -9 4 -2 time another matrix is -3 8 6 -6, sorry, -3 again, 7 -2 -2 -3 -2. Okay, basically it's multiplication to matrix. So first of all, I need to checking the requirement of the multiplication. So the dimension for the first matrix 2 by 3. 2 row, 3 column. 2 row, 3 column. The dimension of the second row is square, 3 by 3. Nice. So that number and that number must be the same. In other words, the amount of column in the first should be equal the amount of row in the second. See, this is different number. It's impossible to perform the multiplication. If you try in GeoGebra or in another device, say no, mismatch dimension. Entonces we get a new matrix, the dimension is 2 by 3. Where come from 2 and 3? One of these two is these two, and this 3 is this 3. Okay? How you doing that? You put in GeoGebra, you type in this, and you create matrix in, I don't know, 7. And you type in this, and you create another matrix in 8. And you type in CAS in 7 times, so the classical symbol of the keyboard, que es multiplication, que es after. Pero in CAS is expressed like that. You press after, however, you see one period and A, and you get this answer. And this answer specifically in this problem is -11, 90, -14, 19, -38, and 50. Okay. We have time. Yeah, we have time. Let me show you in CAS. Let me show you in CAS. There you go. Okay. Look, I did that. In GeoGebra. Okay. Still, I see whiteboard. Okay. I see. Now? Good. Okay. Entonces, let me see where. Yeah. I typing. Look at that. I typing one matrix here. 3, 6, -8. I typing another matrix here. Not in the same line. You type in any place here. You select, right click, create matrix. Entonces en CAS. Okay, in CAS I put it here. Look at that. In CAS I put M8 times A9. And you get the answer. That's it. Super easy. Super easy. Super easy. No big deal. Let's come back. Whiteboard. Let me see now 34. 34 is you multiply 2 matrix also 2 -8 1 6 0 1. Okay, by the way, the dimension is 3 by 2, 3 row, 2 column. Time minus 3 to 1 minus 1, 6 or 1. Okay, it's exactly the same dimension. But it doesn't match it, this number and this number. Therefore, we cannot do the multiplication. The answer is no apply. Okay? Be careful. Let's do it now the inverse matrix. Any questions so far? Any questions so far? I know, okay, I'm doing too fast, guys, but this is a review, no? Let's practice a little bit now inverse matrix. Let's do one example by hand. This is a question 35. One matrix is given 4, negative 1, 5, 1. Yeah, you need to find the inverse matrix. That's the idea. Okay, this is a matrix, no determinant, because it's no absolute value, it's a bracket. So you compute first the determinant of A. Okay, it's 4, negative 1, 5, 1, multiplication this number and this number, okay, 4, multiplication this number and this number, and extra negative, this is positive. Entonces es 5, entonces 4 plus 5 is 9. And this is the factor that you need to divide. And the rest is easy. The rest is inverse matrix is the algorithm in 2 by 2 is you interchange 4 and 1, you put 1 here, 4 here, and 1 and 5 stay the same but opposite sign. This is positive, this is negative. And what about this 9? You divide outside or 1 by 1, get the same. This is the inverse matrix. Guys, look, this is you can see now the differences between determinant and a matrix. In this case, I am divide or multiply by 1 over 9. So basically, when you multiply by 1 over 9, it's divided by 9. One matrix, you multiply or divide every element inside this. This is the multiplication matrix or division by scalar, by just a number. And determinant, no. And determinant, you multiply only one column or only one row, and the value of the determinant is affected by this. Okay, this is the difference. We can use in GeoGebra. Of course, we can use in GeoGebra. And GeoGebra, you type in this original matrix. Look. And you put invert like that. I don't know, it's weird. Invert. Suppose que when you right click associate with the matrix N9, invert N9, and you press enter, and automatically you get the answer. Let me show you one more time in GeoGebra. It's okay, GeoGebra. Wow. Good. Share screen. Okay, where I did. I suppose I did here in the matrix 10. And the matrix 10 is this matrix. Look. Okay, I found. Do you see GeoGebra? Do you see or no? Guys, answer me. Okay, good. I type in the number, get 4, negative 1, 5, 1. I select, I create the matrix. The matrix was the matrix M10. Look at that. This. In the cast, I put the invert M10. And you get this. Super easy. Super easy. When it's 3 by 3 or 4 by 4, it's crazy. However, 2 by 2 is relatively easy by hand. Okay. Entonces the student asked me, Professor, entonces, I do by hand in the test or I do it by calculator? Bueno, the rule is, si es 2 by 2, you are doing by hand. Si es 3 by 3, no, you are doing by calculator or software. Okay, let's do it one more. Okay, 36. 36. One matrix given. Okay, is 0, 1, negative 5, 5. I need to find the inverse. The inverse matrix. I need to find the inverse matrix. Okay, no problem. I computed separately here the determinant. Okay, determinant 0, 1, negative 5, 5. So your multiplication this and this is 0. And your multiplication this and this is 5. The answer is 5. Okay, now the rest is easy. The inverse matrix is this permutation 5 and 0, and this stays the same but opposite side. Now divided by 5. Outside or inside? I prefer inside. Okay, sister. Is 1, 5 divided by 5, negative 1/5, 1 and 0. Final answer. Any question? Okay, let's do it now. The two last problem. Okay, 37 and 38. 37 and 38 is another way to solve the system, but using inverse matrix. And remember, the most important formula is 37. The most important formula is, suppose. Let's explain at the beginning. X plus 2y plus 3z equal 4. X plus y plus z equal negative 5. X minus 2z equal minus 6. I don't see, wow, sorry, carajo. Now, Queen, it's okay? Good. Okay, suppose we have this system. And they want, you solving this system by the method of the inverse matrix. Solve the system using inverse matrix method. Okay. And so I need to remember that formula. The formula is capital X, que es the column vector formed by X, Y, Z, is equal A inverse times B. And who is A and who is B? Well, A is the matrix formed only for the coefficients similar to D in the Kramer rule. 1, 2, 3, 1, 1, 1, 1, 0, negative. This is the matrix A. And what is the matrix B? Actually, it's no matrix, it's a vector. It's the same. It's a 3 by 3, it's a square. And when it's a square, it's invertible. B is the vector formed by the right-hand side, 4, minus 5, and minus 6. Okay, 3 by 1. So when you find the inverse matrix, it's crazy by hand, but in the calculator, yes, we can do that. I want to show you in the GeoGebra, and that's it. Okay, it's minus 2, 3, negative 1, 4, negative 5, 2, negative 1, 2, and negative 1. This is my inverse method. The only possibility is using GeoGebra. I want to explain now. So you type in this, you create the matrix, you put invert, and GeoGebra invert, and you find the inverse. And now we come back to the formula, and now you perform multiplication. Multiplication what? Well, multiplication, the capital X, get the vector formed by x, y, z, is equal the inversion matrix is -2, 4, -1, 3, -5, 2, -1, 2, -1 times the vector B is 4, -5, and -6. Let me see if it's matching or not the dimension. This is 3 by 3, and this is 3 by 1. It's obvious matching, and we get 3 by 1. So you get a vector que is expecting, que is this, que is 3 by 1. And when you are doing this multiplication, it's too long and too, not complicated, but long, you get this value, -22, 25. Okay, again, we are doing the multiplication using GeoGebra again. GeoGebra multiplication. Therefore, associate. X is equal -22. Y is equal to 25 positive. And Z is -8. End of story. Let's see more clear in GeoGebra. Let's see more clear. Let me try to find. Okay, here. Let's see. Yes. Okay. Look at that. I share the screen again to GeoGebra. Okay. Do you see? Now show. Look at that. I did that here. I put the matrix A. I create the matrix. Right click. Selection. Right click. Create the matrix. I did that. Where? Here. And 12. I put the matrix B. Create the matrix again. Wow. Is 13. 4, -5, -6. Now in the cast part, you put the matrix invert. Look at the operation. Look at the operation that we're doing here. Invert M12, que es A inverse, time period, and 13. And we get this answer. Fantastic. Easy. Do it by hand. This is very tedious, and we spend maybe 2 days doing by hand. And this is the super easy problem, que es 3 by 3. And CS 15 by 15, you spend maybe 1 year doing that problem. This is the beauty of the computer science and how you apply the mathematics in computer science. When we have one more example, it's 38, but it's the same stupid thing, right? Do you want to get yes or no? No. So my question is, you understand? I know. My question is, how do you feel for this test? Never we feel, say, any test, even the master degree. I remember when I take the master degree, never we feel comfortable 100%. But you have to practice. That's it. Okay. On the review, and you try. And the most important is the idea in GeoGebra, how you put the number, the view, how you create the matrix, how you select the algorithm to solve the matrix, you know? Now I want to send the test right now. And you let me know. Okay, so you receive or no. And once you get that, you can leave. Say goodbye and you can leave. I sent. I got it. Okay. Got it? You got Sean, you gonna leave? Okay. Lusting? Okay. Okay, guys, bye.